Hello, physical science students. We are on week 4 here of distance learning, and we're starting a new unit called Waves. And I'm going to go through the notes with you right now. So you probably have some idea of what a wave is, but the book definition of a wave is that a wave is a periodic disturbance that's transferred through a medium as energy. And waves carry energy through matter or space. You could think of like a wave in the ocean. That's a really good example, obviously, of a wave. It carries the energy. If you've ever been in the ocean or a big lake and got hit by a wave, whether it's like from a wake from a boat or something like that, you know that there's a lot of energy in there. And all waves are like that in one way or another. So they carry energy through matter and space, and most waves will travel through a medium. The thing that matter that wave travels through, that's what we call the medium. So for like example, a wave in the ocean, the medium is the water. Or sound waves, if you are like practicing social distancing and you're yelling at a friend who's very far away, the medium that the wave travels from, sound wave, would be air or the atmosphere. Now, waves that require a medium, they have a special name. They are called mechanical waves. And we'll break mechanical waves down in a second. There's another kind of wave, though, that does not need a medium. It's a light. Any electromagnetic wave or light does not need a medium to travel. So those waves are called electromagnetic waves. So it doesn't just include light, which we can see. It also includes anything on the electromagnetic spectrum that's a wave. So that could be like Wi-Fi or radio or cell phone signals. All of those things are electromagnetic waves that do not require a medium. Electromagnetic waves consist of oscillating electric and magnetic fields, which is not super important for us, but they all travel at the speed of light, which is one thing that you should note. They all travel at the speed of light. Waves transfer energy, so that energy can be used to do things. For example, like there's lots of hydroelectric dams that have the waves come through and they move things to transfer energy into electrical energy. Or it could be like an X-ray. An X-ray is an electromagnetic wave, but it carries a lot of energy with it, but not enough to hurt you if you take the proper precautions. Let's see. So when sound travels in air, the waves get bigger and bigger. And so the energy spreads out over large areas. That's why you don't get knocked over by a sound wave, because there's a large area that the energy is traveling through. Let's see. Waves are related to vibrations, and most waves are caused by a vibrating object. Electromagnetic waves can be caused by charged particles that are vibrating as well. In a mechanical wave, though, the particles in the medium also vibrate as the wave passes through the medium. So, for example, if you've ever been in the ocean, you might notice that you are when the wave goes through you, you bob up and down. Okay, that's the vibration of the water moving up and down one way, and the energy traveling through you. We're going to skip the spring stuff, so we will skip this picture, and so we got two kinds of waves, transverse and longitudinal, and these are both subcategories of mechanical waves. So particles in a medium can either vibrate either up and down or back and forth, and waves are classified, mechanical waves here, are often classified by the direction the particles in the medium move as the wave passes by. So transverse waves have a perpendicular motion. I just described one to you. A transverse wave is a wave that particles travel up and down, and the wave travels left and right, let's say. So a good example, like I said, is if you're in a lake or if you're in an ocean and a wave is coming towards you, the water moves up and down, but the wave passes through you. So that is a good example of a transverse wave. So the wave moves one way and the particles move perpendicular to that. Longitudinal waves, on the other hand, have they move in a parallel motion. Oopsies. No. There we go. So longitudinal waves, they'll move the same direction. Why is this happening? Closer. There we go. So sound happens to be a longitudinal wave. If the sound is traveling back and forth, or let's say if you were screaming at two people, you're screaming over a distance at someone, the particles, when you scream like that, they go in the same direction of the wave, so parallel to the direction of the wave motion. So opposite of a transverse wave. Again, transverse waves and longitudinal waves are both examples of mechanical waves. This is not for light waves or electromagnetic. This is a good example of what a particle in a wave looks like. You can see the ball sort of travels in a circular motion when a wave passes through it, and that is what a good example of a transverse wave looks like. Okay, and the next lecture we'll go through the different parts of the wave, which we'll get to later. But what you need to know for right now is that there are, if we go back up to the top and just kind of review, these things called waves. Waves travel through a medium. There's two kinds of waves, mechanical or electromagnetic. Electromagnetic wave is one that is like light or a radio wave. Visible light, infrared light, gamma rays, X-rays, all of those are electromagnetic. And then you also have waves that are mechanical waves. And mechanical waves are ones that vibrate as the wave passes through the medium. And there's two kinds of mechanical waves. We have transverse, in which particles go up and down and the wave goes back and forth. And then we have longitudinal, in which the particles go the same direction as the wave. Okay, thanks so much. Bye.